Okay, welcome to another Stat 432 video where we're going to talk about nonparametric classification. Although that's far too broad of a topic, what we're actually going to talk about is specifically estimating conditional probabilities using k-nearest neighbors and using trees. Okay, let's get started, which means I need to get rid of my face. Goodbye. All right, so this slide here should more or less indicate the setup that we're in, which we talked about in the last video. And the data on the left is not necessarily the data on the right. This is all just generally representative of the data we'll see in a classification task, which most importantly, we have this categorical response here. Okay, and so what we said last time is the type of questions we want to answer or ask are, what's the probability that y is pink here versus blue here versus gray here? What about here? What about here? What about this exact point here that's labeled in black? That's the one we're going to talk about in depth in the next slide, but that's the general idea. First, k-nearest neighbors. The idea here is almost so simple that writing it down, honestly, I think sometimes confuses folks. So what I have on that first line there is the expression where the summing is over, like we've seen before, the indexes for the observations with xi values that are the shortest k distance to the value k x that we talk about. But that's a bunch of mathematical notation. Let's just sort of think this through. So what we want to do is use k-nearest neighbors with k is 5, and we want to evaluate the point x1 is 0.5, x2 is 0.8, which is right about here, which I should indicate in black. Okay, cool. So what's the next step? Well, the next step is to find the 5 nearest neighbors, which I believe are here, 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 and here. I'm pretty sure I didn't actually get out a ruler and measure this, but I think visually that's close enough and no one would disagree with me. Okay, well, now I want to estimate the probability that y is A, or blue, given that x is 0.5, 0.8. Well, there's 5 neighbors. 3 of them are blue. How about 3 over 5? If we went to B, or pink, there's 5 neighbors. 1 of them is pink. 1 over 5. If we talk about C, or gray, there's 5 neighbors. 1 of them is gray. How about 1 over 5? Hey, that's pretty easy. So much like regression, the whole ball game is, well, how many neighbors are going to use, and how are we going to define distance? Unless we say otherwise, we're talking about Euclidean. And then we're sort of doing an averaging, except now we're averaging whether or not the y is the color or category that we're interested in. I did make one note here, is that if we're doing binary classification, there's this general wisdom to use an odd value of k. That way we would avoid ties. Can there be ties in other areas? Yes, like we could have ties with this 3 category classification problem we have. How do we deal with them? Honestly, half the time the answer is flip a coin and pick between the two. Sorry, that is ties when we're making the resultant classification. Like, so here we would classify to A if we had to. Right. So, and then this how do we avoid ties business, note that it's going to largely depend on who's implementing the k-nearest neighbors algorithm that you're using. So you will want to check your documentation on whatever function you're using in whatever software you're using to do this. But know that in the binary sense, we can just avoid this by never using an even value of k. Okay, so the rest of the time we'll talk about trees. Okay, so a lot going on in this slide already, so allow me to explain. So on the left, we have some data, 2 predictors, x1, x2, because that's all I can visualize. And then here we do have a binary classification problem where we have two possible categories, pink or blue. And then I'm gonna fit a decision tree model to this. I have in the bottom here a note that I'm gonna use those two parameters we talked about previously, and I'm gonna set min split to be 8 and CP to be 0. These are completely arbitrary. I'm setting min split to be 8 just so I know when to stop, and I'm setting CP to be 0 because I don't want to talk about the math behind it right now. I just want to do some splits and see what happens. And then note that CP has a slightly different definition in the classification setting than it did in the regression setting. It's a little more difficult to talk about, so we won't go into the details, but ultimately it's controlling, well, does this split actually improve enough that we should consider it? Whereas similarly, CP would still say, well, if you don't have this many observations in a node, don't try to split it. Okay, so on the right, I have a tree, and what I've done is simply represented the data in a particular node literally by the partition of the original data set, except for the root node would just be all the data we see on the left here, but that was too much for me to draw, so I didn't do it. So the first split that we see here takes place at an x2 value of 0.3. So that is here. And then if x2 is less than 3, so we go this way. So this is the yes direction to all those conditional statements. This is the no direction. That's an arbitrary choice, but I believe it matches what our part does, which is the package we'll use. Okay, so if x2 is less than 3, we go this way. If x2 is bigger than 3, we go this way. Notice that this matches this, and this matches this. Okay, cool. So, and then what do trees do? Well, they recursively partition, right? So now we could sort of pretend that, like, well, hey, this is the new root node. It's not. It's called an internal node, the way we've drawn it here, which is here. But well, let's split up this. So here, now we're going to split based on the x1 variable. And that would be about here. And now we end up with two new regions, which are seen here and here. But now neither of them have 8 observations, so we stop splitting. And we do a similar thing here to get various things. So here, the next split in this region is a split on x1 is 0.3, which looks, I think, something like this. Right. And beyond that, we split at x2 is 0.8 in this region here, which I think looks something like this. So that's our resultant partition of the original space. Okay, cool. So you might sort of see what starts to happen here, right? So let's say we want to make a prediction at 0.5, 0.5, which I think would be about here, right? Well, 0.5 for x2 is bigger than 0.3, so we end up here. 0.5 is bigger than, is that 2 or 1? That's x of 1. Is bigger than x of 1, so we end up here. 0.5 is less than 0.8, so we end up here. So we're in this node here, which, again, we already saw visually over here, but I'm just noting that down the tree we go like this to get here. Okay, now let's ask some really silly questions. If x1 is 0.5 and x2 is 0.5, which is here, should we predict blue or pink? And again, I think you're all yelling at your computer monitors, well blue, right? There's only blue in that region, so blue seems to make the most sense, right? You wouldn't be wrong. What if we had a point here, right? So we ended up down the tree like this. What would you predict? And I bet you're screaming pink. And I bet you're going a step ahead and saying, well, beyond that, the probability that it's blue is 1/4. The probability that it's pink is 3/4. To which I would say, yeah, you got it. Good job. All right. So let's be a little bit more specific about some of that, though. So inside the nodes, we could look at the proportions of the different categories. So here I've drawn an arbitrary root node and then 2 splits. So we can talk about sort of the probabilities we would estimate for data that falls into an individual node. So in the root node up there, well, there's 8 observations, 4 of which are blue. So we'd say there's a 4/8 or 1/2 probability that an observation in that partition would be blue. And I think it would be 2/8 for pink and 2/8 for gray. No surprise there, right? The math on the left here says how I'm doing this, where A is some arbitrary area or partition, whatever you want to call it. But I think it's pretty easy to see what's going on here, and the math probably just makes it harder. Okay, but now let's say we split this. That seems to be a split sort of right down the middle there. So this new node on the left, well, that seems to be all blue, so sort of no surprises here. We're not going to estimate any probability for pink or gray. And then similarly in the right node, well, there's no blue in there, so nothing there, but then 2/4 for pink and 2/4 for gray. So let's pause and think about this for a second. Or actually, no, let's go back. So what I said earlier on this bigger tree diagram here, so in this node here, this would be a probability of blue that we would estimate to be 1/4, and a probability of pink that we estimate to be 3/4. And we can see how if you end up in different nodes, we would estimate different conditional probabilities of the response given the x values that put you in those nodes. Okay, but back here now. So something to notice is that in the root node, before we split, we kind of had dispersed probabilities. Yeah, there was a higher probability of blue, but there was also these probabilities on pink and gray that were sort of, non-negligible, right? But then we split. And the left node is all blue now. There's nothing but blue in here. So now we have 100% probability here and 0 probability here. That's kind of nice. And over here, well, there's nothing on blue. It's still 50-50 for pink and gray, which isn't great. We'd have to flip a coin to make a classification. But it seems to be better than this. So we need some way to quantify this, though. So I think it's very clear to say that we don't like this when we compare it to this. We'd like nodes to look more like this than like this as a result of the splitting. So to be clear, I think the splits I made here make sense, but I haven't justified them to you in any way. So we're going to take the idea that we just talked about here and sort of use that to quantify what we like and don't like about the resultant partitions from splits. Okay, so to do that, we need to talk about impurity measures for categorical data. And impurity, you can just think of as variance. So what we were doing when we were tree splitting in the regression sense is we wanted partitions with small variance. We wanted all the y values to be really close to each other. Well, the same thing is what we want here, except we want a lot of the same color or category. That's sort of how we're going to think about that variance. We don't want a lot of different colors in the same node. Okay, so there's essentially 3 ways to do this here, and the pink is entropy, the blue is error, and the black, which I'm going to highlight with gray, is called Gini. So these are 3 different ways to think about the variance of a categorical variable. And I want to just highlight Gini for a second, and this plot down here. And these are not necessarily to scale, but I just want to think about the black curve, right? So we're looking at, so let's just say we're varying some p, which is a probability, for a particular category. We're not talking about all the categories yet, between 0 and 1. And it reaches sort of the maximum variance at a p of 0.5, of 0.4. That's probably something you've seen before when you're talking about maybe binomial looking things. You can bound some things by a fourth there. But anyway, so these are all 3 different ways of doing this. Long story short, we're going to use Gini pretty much, unless we say otherwise. You'll see other folks fit trees with entropy. You'll almost never see people do it with error because It's harder to develop pure nodes that way. We're not going to show that, but it's just something to know. But yeah, so basically you sum up this probability of the category times 1 minus the category for each category, and that is some measure of variance. I wouldn't stress about this too much, but just know that we can basically measure the variance within a partition. Okay, so I will belabor the point a little bit and sort of very quickly here calculate Gini for 3 different possible nodes we might see, right? So the first one, pretty clear. There's 6 points in there, 4 of which, no, gosh, that's not clear at all. It's 6 of 6. There's 4 of 6 blue in this one, and there's 2 of 6 blue here. For the pinks, well, there's none in here. There is 1 out of 6 in here, and 2 out of 6 here. And grays, well, none there, 1 there, and 2 there. Okay, so without even doing the calculation, that first node on the left, that is what we would call pure. It's only blue, so it has no impurity. So really, by any of these metrics, you're going to end up with 0 for this variance measure, but we're going to look at Gini. So the second one, we'll just kind of do the Gini calculation that I've already written down here. So this is 4 of 6. This is 1 of 6. This is 1 of 6. So it has a majority. It has, mostly blue and then some other things. So there is some variance, but it does have a majority. And if we compare that to the furthermost right here, well, it's 2 blue, 2 gray, 2 pink. So they all have the same probability. So we see a Gini of 6.6 repeating, of course. So that is the most variable, the most impure. So we like this one the most, this one the second most, this one the third most. Okay. But, excuse me, that still doesn't tell us how to split. So how do we split? So this diagram on the right that I have here, we have some initial partition A, and we want to partition it into a left partition and a right partition. You can call it a partition, an area, a neighborhood, whatever you want. But ultimately, what we want to do is both find a feature variable and a cutoff value of that variable that produces a good split. Well, what is a good split? I've written the expression here. And you can sort of think of this very similarly to that sum of squared error. We were adding those 2 sums of square errors together in the regression sense. So you can look at it this way. Well, the Ginis, well, those are sort of the variances of the different possible, new nodes. So I'll say variances. But there's this term out in front here and here. And what this is, for example, the one on the left, that's the size of the left node divided by the size of the original node. So we're seeing, what proportion of the new values end up in that left node. So I would call those weights. Because we want to worry more about a node that has more observations in it. But so ultimately, you go through each of the variables and try all the possible splits, which isn't actually that hard to do because there's only so many splits because you only have to try the midpoint between all the possible values. And you find the one that makes this the smallest, that is, it sort of reduces the impurity of the original node by splitting it into 2. So that's the idea there. So we're not going to go through the insane calculations here, but I just want to get you thinking about, well, which of the 2 following splits would we prefer? Would we like this one better? Which I think might be the natural one. Well, we get majority pink on the top, majority blue on the bottom. That seems to be good. Or do we want this one? So it kind of is a mix in that top partition there, but it's a totally pure node in the bottom. And so turns out that we like this one better. This one has a smaller Gini. I'm really nervous. When I say smaller Gini, I mean this expression here is smaller for the right split than the left split. I'm nervous to write this down because if I did my math wrong, it's going to be forever written down in this video. But I believe if you do the calculation of the two Ginis here and the weights and do it all, you get 0.416 for this one, and you get 0.4 for repeating, of course, on this one. And we like the smaller one, so hey, that looks good. But the intuition there is that while yes, the one on the left, it gets you a majority pink and a majority blue partitions, the one on the right creates an absolutely pure node. And we like that because then future partitions are going to end up more and more pure. Not that we couldn't further split the other one to end up with pure nodes. It's just if we want to create pure nodes because we're going to keep splitting. So if you get a pure node done, well, then you don't have to worry about it anymore. Okay, so lastly, I just want to remind you that the way we're going to do this is in R. And to fit k nearest neighbors, we're going to, again, look at the caret package. But this time, for classification, we'll use knn3, which is a function specifically for classification, instead of knreg, which is for regression. I don't know where the 3 comes from. Maybe it's the third iteration or something. I'm not sure. For trees, we're going to use the same exact function from the same exact package. Interesting. So this is where it's very important that you make sure your response variable is a factor. Otherwise, if you have a response variable that's like 1s and 2s and 3s, it'll think it's numbers, even though those might be representing categories. So again, I said it before, I'll say it again. Make sure your response variable is a factor. Oh, I'm going to turn my camera on and say it one more time. I'm going to turn my camera on and make it really big. Wait, no, I have a way to do this fast, don't I? I'm smarter than this. Nope, I'm not. I'll have to do it the long way. But I'm going to talk to you for a second. When we're doing classification, make sure your response variable is a factor. I don't know where to look. I need to look like there, I think. Okay, anyway, that's enough of that. So, once again, as always, if you made it to the end of the video, good job, and I'll see you in the next one.